Hello, everybody. This is Czeczuga of Bozilla Corporation. Today, I want to talk about cooling line design and simulation and how a lot of cooling line designs are validated in simulation. And what I'd like to do is discuss exactly how that's done. And what you see on screen here is a cavity side design only on a 2-cavity tool. There's a left and right side cavity, but the cavities themselves are not applicable. We're just talking about cooling efficiency and cooling design. So typically in Moldflow, we place the Moldflow analyst. They'll design the cooling lines as provided by the tool shop, and they'll place an inlet at a specified inlet, whether it's provided or not, and then they will place an outlet. On this particular design, we've also added hoses to make sure there was a complete loop on the cavity side. Now, when we look at this design here, when we analyze in Moldflow how we're going to set up the cooling, it's based on a minimum, most of the time it's based on a minimum Reynolds number. We want to have turbulent flow, and in Moldflow, ideally, that number, you want that to be at least 10,000 or above. Realistically, turbulence, the onset of turbulence is between 2,500 and 5,000 for a Reynolds number. Guaranteed turbulence is suggested to be at 8,000 or above. And for Moldflow, all users typically use the default input of a minimum of 10,000. So on this particular analysis, this design, if we look at the Reynolds number, we can see that the bottom of the scale, 10,000, applies to almost all of these circuits, okay? So if we query these circuits, I mean, that is the minimum number we're getting across there. So this is ideal. Where the cooling lines choke down on fittings, you'll see that the flow rate goes up, or the Reynolds number goes up based on a constant flow rate. And in the hoses, it goes back down a little bit because of the diameter is a little bit different. But ideally, we want at least at 10,000 in the cooling lines, and this looks wonderful. Okay, now, I guess the big question is, does this translate over to the floor? Because what's missing here is the manifold. So how is this going to respond once it's hooked up to a manifold? Well, what we like to do is we highly recommend and suggest that you look at the circuit pressure plot. All right, what's important about the circuit pressure? If we look at the pressure plot, if they're not uniform, these are all different. How many times more is the bottom circuit, the red circuit, versus the circuit above its blue circuit, and so on, okay? So like for this green circuit, the red circuit requires twice as much pressure to push the water through than the green circuit, and many times more on the blue circuit. So when these are all hooked up to a manifold, the circuit that requires the most pressure, now they're all hooked up to the same manifold, delivering the same flow rate, well, delivering the same pressure, really. So the circuit with the highest pressure demand, this 1.125, will probably receive the least amount of flow because there's a lot more pressure requirement for it than a simple circuit that requires only a little bit of pressure. So if we look at the flow rate here, not hooked up to a manifold, so the flow rate through the circuit that has all the baffles, has the highest pressure demand, is 0.9 versus the most simple circuit, 0.9. Okay, that's exactly right. They're all uniform. I mean, look at the scale. These aren't hooked up to a manifold, so they all require the same amount of flow rate to get the Reynolds number we're looking for. So we'll look at that again. They're all the same Reynolds number. That's perfect. All right, now what happens if we hook this up to a manifold? All right, for purposes of this discussion, we set an inlet specified not at a minimum Reynolds number, but it was at a flow rate. Realistically, on the floor, very, very high flow rates are used to ensure turbulent flow through all of the circuits. Now, that's smart, but it's not efficient. We would like to use the least amount of flow rate, the least amount of energy to push that water through the circuits, and yet still have efficient cooling. So if we said, let's just use 5 gallons a minute to go through these circuits, what does that mean? Let's look at our Reynolds number. Okay, the circuit with the biggest pressure drop with all the baffles It requires the most pressure, and because of that, it has, well, they're all coming from the same manifold, so the least amount of pressure is going to get most flow, all right? And the Reynolds number on the simple circuit is just about 15,000, over 14,000 Reynolds number. And for the complicated circuit with more pressure demand, it's barely turbulent at 74, just over 7,400 for a Reynolds number. Now, if we look at that same pressure through the circuits, what's the pressure demand? Okay, if we compare these, okay, so there's a significant amount of pressure, increased pressure requirement for the long circuit with all the baffles. And because of that, your Reynolds number decreases when hooked up to a manifold. So is your cooling efficient when it comes to your circuits once it's hooked up to the manifold? So we're taking a simple design from Moldflow, or an analyst using a cooling design in any flow analysis, and saying, okay, we're not hooked up to a manifold. We're just going to look at each line independently and even have hoses look at the circuit independently. And we say this is good enough because the minimum Reynolds number is 10,000. But is that true once it's hooked up? Well, if we just use 5 gallons a minute on the inlet, we can demonstrate how it's not sufficient. Okay, so all circuits are not created equal once hooked up to a manifold. Okay, that's the most important thing here. So now if we take that inlet and increase the flow rate to 10 gallons a minute, if we double it, okay, we can then see that our Reynolds number, and this is what's typically done on the floor when these manifolds are hooked up to water. I mean, some of these are 50 gallons a minute, so it's exceptional, but it's, again, it's not efficient. It's a tremendous waste of water. So if we just went up to from 5 gallons and doubled it to 10 gallons, all right, now we're getting our turbulent flow in the most critical circuit, if you will. The one with the most baffles has the highest pressure loss, but now we're getting at least 15,000 in there. So we really had to jack up the flow rate. By all intents and purposes, that doesn't seem like to what's normal on the floor. But if we're to look at this from an efficiency perspective, this is very inefficient. We want all circuits to have the same pressure drop. So what do we want to do to the circuits? Now, if I take a step back and we look at Moldflow design in the circuits, I say Moldflow, but any cooling analysis software, you really want to incorporate the manifold. But if you don't incorporate the manifold, what you want to do is make sure that each circuit, this circuit pressure plot is one of my favorites. We want to make sure that each circuit, they all have the same pressure loss. So you have to route them differently or double or triple up circuits so that those double or tripled circuits are about equal as to the worst, the highest demand circuit with the highest pressure drop. And once you do that, then once you hook everything up to the manifold, there's not going to be a circuit that takes all the pressure. The simple circuit takes most of the water because there's no pressure resistance, okay? None. The circuit with the highest pressure resistance received the least amount of flow. So it doesn't cool as efficiently. The one that needs the best cooling has the worst cooling because of that, because it's not getting the flow it needs. I'm going to restate that because that's the crux of this discussion, is that the circuit that requires the most cooling is getting the least amount of flow rate and the least amount of cooling. Okay, so combat that, we look at all the other circuits and we hook them up so that our final completed circuits should all be about balanced, about the same pressure drop. And this way, once they're hooked up to a manifold, then they have the same amount of flow rate and they all have the same amount of Reynolds number, turbulence, and cool as efficiently as possible. No one circuit is lagging more than another. This plot right here is one of my favorites. We emphasize this in most of our meetings and discussions because there's not a lot of emphasis put on this in tool design. A lot of tool designs really focus on, putting enough, cooling in the tool, baffles, bubblers, Gundra locations, the circuit locations. But rarely do we talk about balancing the circuits. I'd really like to emphasize that and maybe change how the industry looks at cooling design. All right, that concludes this discussion. Take care now.